trig equations. So let's go through all the different formulae, identities, call them what you will. So we start off, I guess, with our compound angle formula. Sine, cos, cos, sine. If it's the sine, it's the sine. Cos, cos, sine, sine. If it's not a sine, it's not the sine. And then tan plus tan on 1 minus tan, tan. Then from there, we worked out double angle formulas. So sine 2 theta, 2 sine theta, cos theta. Cos 2 theta, which we did talk about yesterday in the integration, but it can be written in one of three ways. Cos squared minus sine squared. 2 cos squared minus 1, which allowed us to then go and integrate cos squared if we wanted to. Half outside of 1 plus cos 2 theta. And the other form, 1 minus 2 sine squared theta. And if we wanted to work with sine squared, well, sine squared's a half of 1 minus cos 2 theta. And then tan 2 theta, 2 tan theta on 1 minus tan squared theta. From there, we then went from double angles to, I guess you could call them half angle results, or the T results. So if T is half the angle, so theta on 2, then tan theta will be 2T on 1 minus T squared. Sine theta 2T on 1 plus T squared. And cos theta 1 minus T squared on 1 plus T squared. Products to sums. So we get 2 sine A cos B is sine A plus B plus sine A minus B. And then you have the cos cos, and then you have the sine sine. Or, another way of thinking about sine sine, and I know you think, well, hang on, all he's done is swap it around, but I've swapped it around for a logical reason. Because you'll notice by writing it as minus cos A plus B plus cos A minus B, then the first one is always A plus B. The second one is A minus B, so it makes it a little bit easier to remember the formula. How do I know what ratio? Well, think about where it came from. Sine cos must have come from the sine expansion, because we went sine cos, cos sine. So they're both sines. Cos cos must have come from the cosine function, because when we expanded that out, we got cos cos. And we also got sine sine, so consequently the second one is also from the cos expansion, but we put a minus out the front because clearly they can't be the same as the cos cos. So the sine sine, one of the ways I think about it is, well, hang on, sine sine, oh, well, that's a bit different. There's a negative out the front. Then, of course, we could go back the other way. The sums to products. 2 sine half sum cos half diff. 2 cos half sum cos half diff. And minus 2 sine half sum sine half diff. Now, I've put an asterisk there, whether you may or may not recall. Products to sums is in the syllabus. Sums to products is not. But you never know, could come in useful. If they specifically wanted you to use the sums to products, I would expect they'd start the question off with, either they would give you the formula in the question, or they would ask you to derive it. That's what I'd be expecting anyway. Products to sums, of course, should be on the reference sheet. Pretty sure it is. Okay, solving trig equations then. At the end of the day, we just want all the angles to be the same. So if we've got a mixture of thetas and 2 thetas, get them all to thetas, or get them all to 2 thetas. We want the angles the same. Then, of course, they will tell us some sort of range to find answers between. We want that to match what we've chosen the angle to be. So if I've changed it to 2 theta and they've said go between 0 and 360 for theta, then I'll go between 0 and 720 for 2 theta. And then try and get the trig functions the same. So all the same ratio, all sines or all coses, because then essentially it's just an equation and the pronumeral is that trig ratio. If ever in doubt, just go through and change everything to sines and coses and see what happens. Obviously, check your answers, as you always should be doing anyway, but when you change an equation, remember, in solving it, then sometimes you'll create new answers that are answers to the new equation, but aren't necessarily answers to the original equation. So you do need to check. All right, let's start off with a very simple one there. Cos 2 theta equals a half. They've told us it's going between 0 and 360. So, okay, it's already a single trig ratio. I can work with that. but I'm dealing with 2 theta here, so I'm going to go from 0 to 720. First and fourth quadrants we're dealing with. Cos is positive in the first and fourth quadrant. Just draw myself a little diagram there to remind myself what's happening with the acute angles. So the acute angle is 60 degrees. In the first quadrant it will be that acute angle, but in the fourth quadrant it'll be 360 minus that. So 2 theta is 60 and 360 minus 60, in other words 60 and 300, but I'm going around the circle twice, so I add 360 to both of those answers. Now those answers are for 2 theta, we want to find theta, so we divide everything by 2, and because we've gone around the circle twice, when we divide by 2, all of our answers end up between 0 and 360. And so we get 4 answers for that particular one. Same question, but now if we wanted to, we could use a double angle result to solve that. And so, well, cos 2 theta is a half. I'll change cos 2 theta to be 2 cos squared theta minus 1. And I'll solve this. And we get cos squared theta is 3 on 4. So cos theta is plus or minus root 3 on 2. So I'm in all 4 quadrants this time. So, let's draw up the butterfly. There it is. So in all 4 quadrants, root 3 on 2, the acute angle would be 30, but I'm in all 4 quadrants, and so, surprise, surprise, I end up with the same 4 answers. So now it gives us an alternative way, I guess, of solving that question. Which way would I go? I'd probably just go the first way on that one myself. Okay, 4 sec squared is 3 tan x plus 5. So I've got different ratios. I want to try and get them all. The angles are the same, so that's fine. Let's try and get the ratio the same. But of course we have a trig identity that involves sec squared. And we know sec squared is 1 plus tan squared. So I can rewrite that now. It's all in terms of tan x. It's a quadratic, but it's still in terms of tan x. And it factorizes this one. So I get 4 tan x plus 1. Tan x minus 1, giving me 2 possibilities. Tan x is negative a quarter, or tan x equals 1. If it's negative a quarter, well, tan's negative in the second and the fourth quadrant. The acute angle I'm looking for, well, it's not an exact value, so I've approximated it there to 14 degrees 2 minutes. And we get our 2 possible answers. Tan x equals 1. Well, that's in the first or the third quadrant because it's positive. That's one of our exact values, isn't it? Tan x equals 1. So that would be pi on 4, if I remember correctly. Oh, we're dealing in degrees for this one because it says 360 degrees. Okay, so 45 degrees. We get our other 2 answers. It's not for them to go and put it all together. So you put it all together in one final solution and say, well, here are the 4 answers. Okay. Got a mixture of a few things here. Cos 2 theta, cos squared theta, sine squared theta. So I want to try and get the angle the same, but I also want to get the ratio the same as well. So the cos 2 theta, well, there's 3 things I could change it to. Which one did I go for? Cos squared minus sine squared. The reason I did that one is I'm going to play around with that and get 3 cos squared is sine squared. Divide by the sine squared and I get tan squared. And I've got it down to 1 ratio. Tan squared is 3, so tan is plus or minus root 3. So I'm in 4 quadrants here. The acute angle would be 60 degrees. So my solution is 60, 120, 240, 300. Because the other way I could have done it, well, actually there's 2 other ways I could have done it. I could have changed the cos 2 theta to be 2 cos squared minus 1. And then change the sine squared to be, what would that be, 1 minus cos squared? And that will get everything in terms of cos. I could have gone cos 2 theta is 1 minus 2 sine squared. Then change the cos squared to 1 minus sine squared. Get everything in terms of sine. And the choice, again, it's up to you how you want to approach the question. Here's one from, albeit a long time ago, an actual HSC question. Cos 2 theta is sine theta. Cos 2 theta, I'm going to use the sine squared one, so then my ratio is all in sine. So we get 2 sine squared plus sine minus 1. That's our quadratic, which factorizes. So we have sine is a half or sine is negative 1. Well, if it's a half, I'm in the first or the second quadrant. Acute angle on that one would be 30 degrees. And so theta is 30, 150. Sine theta is -1. That's a boundary value, -1. So I'm just thinking of my graph. That'll be at 270, I think, 270. Yes, 270. Combine it all together, and we get 3 answers for that particular one. Oh, an even older question. 2 sine squared is sine 2 theta. At least it's a different ratio this time. Let's change the sine 2 theta. It's going to be 2 sine theta cos theta. Okay, I can't really make them all the same ratio in this case. But I can write it as a quadratic and then factorise. And this should work because either sine theta will equal 0 or sine theta equals cos theta. Well, sine theta equals 0 is a boundary value. And remember, whenever 0 is a solution, 360 is also a solution. Often people forget to put both of them in. Sine theta equals cos theta, I'm going to rewrite as tan theta. Divide both sides by cos theta. Tan theta is equal to 1. And so we're in the first or the third quadrant now. The acute angle is 45 degrees. And we get our 2 answers. Combine it all together. And there we go. Ooh. Sine theta times sine 3 theta. Now, the temptation is to come up with a formula for sine 3 theta, which of course there is one. I mean, we could work one out, and then multiply it by sine theta. Possibly a better way to do this one is products to sums. Whoa, how do you get it straight over? Remember? Sine, so it must have come from cosine. Sine, a bit different, so it starts with the negative. The first one is the sum, the second one is the difference. Okay, so that's why I got 4 theta in the first one, 2 theta in the second one. Now, well, how on earth has that made my life any easier? Well, 4 theta is double 2 theta. So I could rewrite the cos 4 theta using 2 cos squared minus 1. And now I've got the trig all being the same. But it's now 2 theta, so I'm going between 0 and 4 pi. Okay, let's rewrite all that. Oh, the ones cancel. So we get a nice little one to do there. Either cos 2 theta is 0 or cos 2 theta is a half. 0 is a boundary, but we're dealing with radians this time. So, and we're going around twice. So I've got pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2. Divide everything by 2, of course, to get theta. Okay, cos 2 theta is a half. I'm in the first or the fourth quadrant. The acute angle is pi on 3. So we end up with, again, 4 solutions because we have the pi on 3 and the 5 pi on 3 going around twice. So I add 2 pi to all the answers. Divide those by 2. Then combine them all together. And as a little bit of a challenge, because it is quite fun, when we're playing with radians, it's a little bit trickier. Get them in the correct order. There we go. It goes pi on 6, pi on 4, 3 pi on 4, 5 pi on 6, 7 pi on 6, 5 pi on 4, 7 pi on 4, 11 pi on 6. Don't panic. No, you don't have to get them in the correct order to get the answer correct. But it looks nicer. Okay. Alrighty. So, 11A, let's solve some trig equations.